All right, so let's talk about k-means clustering. This is a wonderful technique, extremely easy and extremely powerful. And it works like this. You make a data set. Now we're going to try and categorize these dots. It's an unlabeled data set. They come in clusters. As you can see, there's 3 small clusters here and 2 small clusters on the right. I just want to separate it into categories. And this, of course, is a very common problem. You run a shopping site. You have customers. You'd like to separate them into groups somehow, like IP address they come in from, the time of day they shop, the previous products they bought, and then decide what product to recommend. So even just separating them into categories would improve my shopping site. So a k-means model is incredibly simple. It goes like this. You decide how many categories you want to have, and if you want to have 5, you just place them randomly out there, and then this is the kind of fit you're going to get. You're going to get these answers, and the way the algorithm works is like this. Originally, you just place them randomly on here. Then you draw boundaries between them. So since I have a center here, I'm going to take all the dots that are closer to this than any of the others and call them a member of this group. So all the ones in this region I'm going to call gray because they're closer to this X than that X, and the same for each of these. So that's a very simple calculation. Then now that I've done this, I now calculate the average position in each of these zones and move the dot to the center. So this is like you have a trampoline with a bunch of nuts on it, and you put bowling balls on it, and they make a dent and then slide down to the bottom. So that now, all I do is now move it close to the center. That will move it in this direction because there's more dots down there than here. And it'll eventually move in that direction some more, so this boundary moves and it quits including those. This one, now that those are included, is going to move to the center. So when it works, it's fast, it doesn't take much computational power, it's very accurate, very effective. I mean, it rocks. Now, there are bad things that can happen. If you have bad starting values, like 2 centers over here and 1 center there, it will never solve that, and it will end up with this solution. These 2 combined into 1, this broken into 2, that's going to be the local minimum it settles into when there's in fact a better global minimum. So when you run this, the way it does it is it starts with 10 random starts and tries to take the best fits, because this is not a best fit. This doesn't have the lowest loss. There is a much better fit available, but you have to start over with different random starting values. So that's the game. So that's cool. This is a very powerful algorithm. Once again, you got a problem of scale. Suppose I multiply the vertical scale by 10. Now, what I'm going to get for a solution is that. Like before, remember, I told it vertical errors are 10 times more important than horizontal errors, so this is not the right solution. It is not acceptable to have this thing sitting here and kick all those dots with this high vertical errors. Instead, horizontal errors are acceptable, even huge ones, but vertical errors are not acceptable also. I'm going to get this answer. That's the problem. You have to scale your data correctly, or you're lying to your model and tricking it into doing the wrong thing. So now, if we make a moon-shaped data set like this, with these curvy things, and then try to fit it, the textbook didn't like this, but I liked it. You fit it with 8, and you'll get this fit. Now, I call this a pretty good fit, but of course, I think I'll just put another layer after it that says, take these 4 and call them category A, and these 4 and call them category B. And so the job is done, but of course, it did not separate it into 2 categories, A and B, not at all, cleanly. But that's an issue there. And so now you can benefit from this in ways that may not be obvious. For example, here's a fundamental problem. You have unlabeled data, and you need labeled data. Now, you could pay humans to label it, but nobody wants to do that. Paying humans, that's a lot of money you're spending. Is there a way to save yourself that time? And there is. So now we're going to take a digits data set. We have another data set of handwritten digits. And here's the first 50 images, and there's hundreds of these images. I think there's like 1,500 total images, 1,400. So you can see the images, and it gives you the answers for all of them. So if I just fit a model to the entire training set, then I'm going to get 90.6% accuracy. So that is using all the labeled data, of which there were 1,400. But I wonder, is there a way to do this without having all the data labeled? So if I just take the first 50 images and train on them alone, then of course it's measurable. I get 74% correct because I had 1,400 images and I only used 50. That wasn't very good. So what you do is you use k-means to form 50 clusters. So you find the images that look similar and cluster them together. And then you go back and find the image closest to the center of each cluster. So now instead of having the first 50 images, I have the 50 representative images that represent each of the classes. And this is what people do with like focus groups in voting. They try to find people that will represent the classes they're hoping. So these are not just 50 random images. These are the 50 images that were the average of their clusters. And then you pay a human to label just those 50. And then train on that. And now you get 84% accuracy instead of 74%, which is much better. But you can do better. Well, now what you do is you propagate the labels to all instances. Since I labeled those 50, I assign that label to all the rest in that cluster. So I only paid a human once, but I labeled all the images, and now I train on all the images, and now I get up to 89%. Now the original training with labeled data got me 90.6, so I'm still not there yet. Now the question is, there are probably some outliers from the cluster that are in the border between two clusters, and they're probably not helping me any, so I remove the outliers. I take the 1% of images that are furthest from the center of their cluster and throw them away. And then I get 90.9%, better than training on the original data. So this is, this shows you how these categorization algorithms can be very helpful in ways that aren't incredibly obvious. So that's the last one of general information about how these models work that I wanted to share.